Broadcast is now starting. All attendees are in listen-only mode.
Good morning, everyone. Welcome to the webinar on SolidWorks Flow Simulation. We'll begin in 10 minutes. I'm doing it on Romans. We will start in a minute. Welcome. Before I start up, I would just like to say thank you for everyone making yourself available for this webinar on SolidWorks Flow Simulation to design for better cooling systems. Let me introduce myself. My name is Chetan. I'm part of Beacon from last 4 years. I'm taking care of the whole simulation suite related to SolidWorks. So the today's agenda would be giving a look at how SolidWorks Flow Simulation can help you in your everyday activities, and what basically the flow simulation mean or the CFD techniques mean who are not aware about it. So to start up, I would like to take you through a couple of modules available in SolidWorks simulation. First of all, what we call them as the SolidWorks simulation products. One is the SolidWorks simulation, what you can see to your left side, which works on a finite element methodology. We also have a module for that. We have a module called SolidWorks Flow Simulation, which is on a CFD platform. So let us start up with the module for today, that is SolidWorks Flow Simulation. So let us give a look at what basically SolidWorks Flow Simulation is all about. We'll also try to understand what do we mean by a fluid flow analysis and why do we have to invest in it. We also have to go through a few real life examples solved. We also have a few industry specific modules followed by a small demonstration, and then a summarize of what we have seen in the overall presentation for today. This would be the agenda for the next 30 minutes, followed by. So basically, what do we mean by fluid flow analysis is nothing but taking out real life fluid problems or heat transfer problems, and then piling it up, and then putting up into your computer, into a virtual environment, and then try solving it by means of a technique called CFD. Is basically related to analysis of flow simulation. So who can basically get a huge benefit out of it is basically the engineers who are working related to any flow of gas or liquids or any kind of heat transfers by means of force methods or natural methods, can definitely get a great benefit by using this technology. What are the advantages of using CFD techniques is basically to reduce your prototyping and the experimental testing, which can definitely lead in a faster time to launch the product. Of course, if you are working on any kind of internal testings, maybe if you are into any kind of aerospace or automotive departments or any product related to racing bicycles or something like that, where you go for a huge kind of internal testings, can definitely be eliminated, and it is definitely less expensive comparative to the testing methods. Of course, we have a lot of ability to investigate more options, like what would be the output if I change a particular parameter like the velocity or some minute change in the design, or maybe a minute change in the material properties, or maybe minute change in the finishing of the object, how it is going to affect the overall output. There are definitely a lot of possibility to investigate, a lot of options. Of course, you have a more better way to visualize the outputs in a much full colorful plots, and much easier way to have an access to give a look at the outputs in detail related to the overall flow domain. Of course, you require very less manpower, because you have to spend more time in more. You have to spend more manpower in any kind of prototyping or testing conditions, because you have to go for the design, then the manufacturing, and then the setup for the whole testing equipment, and then put a lot of sensors and stuff. So you can avoid all such kind of manpower activities. Previously, flow simulation or CFD was basically implemented in later stage of the designs, to especially to validate the designs whatever they have done. But slowly the trend has been moved to, rather than implementing at the later stages of the design, they have started implementing at the initial phases of the design, so that the effort of the engineers is minimized. At the same time, the production is not compromised. So you can see the graph, so that the implementation of the CFD to help avoid a lot of activities have been reduced in the product development timeline by minimizing the efforts. So to be very frank, there are a lot of tools available in the market. So why only SolidWorks Flow Simulation? So I'll just go through a little bit of a couple of examples on that. Especially there has been a big thinking in the minds of engineers that CFD is a very complicated platform or a very complicated tool. So there is always a huge barrier between the design engineer and the guy who works as a CFD specialist. So there is a huge wall. They feel like the CFD is a pure whole set of different technology, and it's very complicated to work, and it is not a tool which is given to the design engineers. Those kind of all kind of thoughts have been provoked into the minds of engineers from long back. But this what SolidWorks Flow Simulation is trying to do is to eliminate this barrier between the design engineers and the CFD specialist. So SolidWorks Flow Simulation wanted to implement such a way that all the design engineers have the tools available to work on at the very basic level of the designs, so that they can definitely make much better products and launch the products in a much faster way. So, few examples. If I give a look at the SolidWorks Flow Simulation, if I relate it to a few real life examples solved in using SolidWorks Flow Simulation, it can be applicable into a lot of industries. So like we can use it in aerospace departments if you are working in any kind of aerodynamic applications. Not only in aerospace, we can also do it in any kind of other applications as well, like automotives or any kind of commercial applications as well. We have electronics module, especially related to electronic side. We'll work on that in the coming slides. Give a look at how electronics cooling can be helpful to you. It can also be applicable to HVAC, room ventilation systems. Not only to room ventilation systems, it can be applicable to any kind of industries related to HVAC. How the flow is actually happening inside the room, whether the ventilator size provided is sufficient enough to give me the better quality of air or not. So the application wise, it are too many. These are just few of them. So these are the few applications. What are the capabilities we have in SolidWorks Flow Simulation? What we call it as a free surface. This has been a new tool which has been implemented in SolidWorks Flow Simulation 2018. So we can basically find out how the things are going to work out on a free surface level. This is one of the very good and powerful tools which have been implemented in SOLIDWORKS Flow Simulation in 2018. We also have a capability to work with internal flows, might be for not only related to valves, but any kind of internal flows. We can also work on internal flow analysis. We can also work on any kind of external flow analysis, anything related to external flow analysis. We also have a capability to work with external flow analysis as well. Sorry. We also have a capability to work with compressible fluids. Any kind of compressible fluids we can work on, like working on any high level Mach numbers where we have a lot of compressible effects coming into the picture. So we can also work on compressible fluids as well. We also have a capability to work on compressible fluids. We also have a capability to work with heat transfers. This would be one of those examples we'll give a look at in the next presentation. I will try to take a similar example to make you understand how the electronics cooling module of SolidWorks Flow Simulation can help you in overcoming the thermal challenges inside an electronic component or any kind of applications. Sorry. We can also work on rotating components, anything related to rotating components. We also have a capability to work with rotating components like pumps or compressors or impellers or something like that. We can also work on rotating components. We also have a capability to work with rotating components. We also have a capability to exchange the results from flow simulation to the structural, because since SolidWorks is the only tool which is integrated on a single window platform, so the methodology of converting the outputs from one module to the other module is as easy as having a button, click at the button at your fingertip. Like I can like for example in the previous slide you have seen because of the flow what would be the deformations, so I can easily exchange the results from my flow and see what would be the deformations or the stresses coming on the structure because of the only as the flow as the load onto it. We can also work on non-Newtonian fluids. Anything related to non-Newtonian fluids, especially into any kind of medical industries, like a flow of blood in any kind of an equipment in the operation theaters you are using, or maybe in any kind of food industries like apple sausage or honey or something like that. Now we can also work on non-Newtonian fluids. We also have a capability to work on non-Newtonian fluids as well. We can also work on time dependent analysis, that is a transient analysis. So we also have a very good features and tools available to work with time dependent analysis. We can also work on quite advanced radiation modules. We also have a heavy radiation modules available. So if you wanted to work on any kind of radiation modules, we can also work on advanced radiation modules as well. So to pile it up in short, we have a huge capability wise. So if you can see the SolidWorks flow simulation, we can work on internal flows, external flows, we can work on heat transfer problems. Like to summarize whatever we have seen, we have a dedicated module for electronics, we have a dedicated module for HVAC, where we can target the challenges where you have a huge challenges in the electronic side, where to remove the thermal challenges by means of any kind of applications. So we have a huge database for that as well. We also have a good modules like heat pipe modules or joule heating modules and PCB generator modules. We also have a module for HVAC where we can do a very good study related to the comfort levels. We have a database for comfort parameters as well. Of course, we can work on advanced radiation as well. So this is the overview what SolidWorks Flow Simulation can offer you. To come up with the applications of these verticals, applications of these tools, it has been applicable into a lot of industries for SolidWorks flow simulation. You can see electronics 23%, valves industry 16%, a lot of applications like aerospace, education, transport, machinery, medical, so whatnot. We can there are a few things there are a lot of things what we can do a lot in a lot of industries. So coming up to the advanced modules, we have got electronic cooling and HVAC analysis. So let us give a look at the electronic cooling, because today we are focusing on the thermal challenges related to electronic side. That would be the agenda for today's presentation. So I'll take you through a little bit of technical info related to electronic cooling. For any other information, you can please contact us anytime. For any kind of other information, like for HVAC, if you are interested in HVAC, you can let us know. We can come down, discuss with you, and showcase the capabilities related to HVAC to you if you are really interested on that. So electronic cooling design module, it's an industry specific tool where dedicated simulation tools for thermal management studies for electronics department or electronics design side. Companies who are facing thermal challenges with their products and definitely require a very accurate thermal analysis of their electronic enclosures can definitely get more can get more benefit out of these particular tool which is there with the SolidWorks flow simulation. Then in this particular module, we can basically see the engineering challenges to overcome the thermal studies by predicting a better airflow inside the electronic enclosure by making it in a much better way or optimized way, so that the right amount of ventilation is provided. Definitely we can see the components which are generating more heat, and which what it needs is to dissipate to avoid over risking. So we can definitely give a look at the temperature as an output. We also have heat sink selections to make it a much better heat sink designs. We also have better fan selections as well, so that we can give a look at how the fan is behaving with respect to your design, whatever we have provided. Not only this, we also have a conjugate heat transfer capability, so that we can work on conjugate heat transfers as well. We also have a very powerful tool called two resistor component models, so that we can describe the thermal behavior of the chip, with its interconnection with the PCB boards and the environment. We have a fully supported two resistor models according to JEDEC standards. We also have a module for heat pipe compact model, definitely one of the most effective heat removal systems. We also have PCB standards. We also have a PCB module available according to your applications. So if it is multi-layer PCBs like 4-layer or 8-layer, so we can also define those layers to give a look at how the PCB is working out with respect to the thermal or application point of view. We also have a capability for joule heating as well. In the joule heating, we can include the heat transfer calculations by means of conversion of electricity into your temperature as an output. We also have a huge database for the library. We have a huge database for the library available for different kinds of materials, and of course we have TECs. We have fans. We have solid materials. Of course, you have the leverage of customizing your material database according to your requirements as well, if you want. So if I go and give a look at the product demonstration, I would like to, before I start up, I would like to say, if you have any queries, please feel free to put a message to me. Please feel free message. No, please feel free to put a message to me. So I'll just wait for a few seconds to see if someone has any queries till now, or else we can continue with the presentation. Okay, I think there are no questions. That's good. So that means you're following me. Thanks for that. So let us go with a product demonstration related to electronic side. I will try to take an electronic enclosure to make you understand how can we predict the thermal behavior inside electronic enclosure. So this would be the example what I'm trying to take now to work on for the product demonstration. For this example, I have a requirement saying that there is a chip and the maximum chip temperature allowed is 104 degrees centigrade. So anything more than that is not allowable for me in this design. So now I wanted to make sure that the temperature of the chip is not going beyond 104 degrees centigrade. So to make sure that my temperature inside the chip is not going beyond the limit whatever I wanted to give, I have several conditions to work before. So I wanted to give a look at sorry. Please let me know, can you see the screen? Okay. Yes. So to give a look at how the temperature should not exceed beyond 104 degrees centigrade, I wanted to now play with couple of my parameters. One is the heat sink design, which heat sink is better for me to maintain the particular temperature of 104 degrees centigrade, and whether I have to go with one fan or two fans, and at what would be the location of the fan to reach that particular optimal temperature or the limited temperature of that particular chip, whatever I wanted. So let me quickly take you to the SolidWorks interface. So this is how my SolidWorks Flow Simulation tab looks like. So once you go up with your design, whatever you have, I can make multiple configurations of the design. So who are already aware of configurations, have made multiple configurations. You can see there. This is the flow simulation tab. If you can see, this is what I call it as a single window integration. So I can work on the flow simulation right away on my design platform of whatever the design what I have done. So in the flow simulation, firstly I go with the setup, what I call it as a wizard. So in the wizard, I go and set up the project. Like what would be the kind of analysis you wanted to perform. So let me say I wanted to perform this is with heat sink 3 and one fan. So that would be the name of the study what I define. So if I just go, it's just define the standard set of units, whatever you wanted to work with, define what kind of analysis you wanted to go with, internal or external. You wanted to include transient analysis. I can go with time dependent. If you wanted to include heat conduction, of course, heat conduction in solids plays a very key role. And you wanted to work with radiation, I can also work on radiation modules as well. If I go with what kind of solids or gases you wanted to play with, I can define them. Okay, so I can just give the setup accordingly and then proceed ahead. So I have just done a simple setup for that. So if you can see, I have made a setup for that. If you can see, I have defined my domains, and I'm trying to define the solid materials, because I'm definitely heat conduction and convection both plays a key role in the electronics. So what I've done is I've gone ahead and defined all the things. So if you can see, these are the different components what I have. So if I'm trying to expand my tree, so I've defined a few materials. This is made of some stainless steel, which is highlighted in the blue color. If you can see, I have defined a few things with the copper material. Now these are preset standard materials. So I just right click and insert a solid material and select the particular property, and I go to predefined and choose what kind of things you wanted to define, and so just apply to it. It automatically takes up those materials. So I've defined predefined things. So if you can see, I have also defined a PCB which is actually made of a 4-layer. If you can see, this is a PCB board which is made of 4 layers. So we can also work on 2 layers or 8 layers also if you want. Let me say you wanted to go ahead and work on any kind of advanced layer of PCBs like 16 layers or something like that. We can also customize the PCB properties accordingly to that. So that is basically available in the engineering database. So if I go to my engineering database, so I have got PCBs, PC printed circuit boards. So if you can see, if I go to the item properties, you can define the conducting layers, how many number of layers you wanted. So I'm defining the number of layers as 4, for example. So the first cover is what thickness and what percentage of copper is defined in it, and second stage and third stage and fourth stage. So I can define my conducting layers in the PCB board. I can customize my PCB board. Not only my PCB board, I can customize a lot of things. So I can have a heat sinks. You can see I have a predefined heat sinks. So if I go to the properties, I have a predefined heat sink. If you want, you can go and make your user defined heat sinks. I've got the predefined fans. I've got a lot of fans in it, axial fans. So if I just try to expand, huge database, standard fans. So I go to the properties, huge database of the fans. I've got what would be the flow rate available for the fans. So basically this is nothing but fan curve. So not only the fans, I can also have a huge database for my solid materials as well. So if I go to materials, I've got solids. So I've got the predefined values like alloys. In the alloys, I've got standard materials. If you go for building materials, I've got building materials as well. If you wanted to go for polymers, I've also got a material for polymers as well. But you can also customize your material properties according to your requirement. Not only for the solids, we have got materials for the gases, liquids, compressible liquids as well. So just save it and start using it according to your requirement. Okay, so I've defined my solid materials accordingly to that, and I'm defining my boundary conditions. Let me say this is the place where I have the opening. So this is just nothing but environmental pressure. So this is nothing but an opening, whatever I have. So are we lacking on the screen, I guess? Okay, I think we are on time now. Okay, so I have defined an environmental pressure. If you can see, I have an environmental pressure defined there, and I have defined a fan. There is a fan which is given out there, and this is an outlet fan, and I have defined a fan, and I have defined the heat resources. Because for me to understand the temperature plots inside, the first thing what I would require is the heat resources. What would be the heat generation rate from each part? So if you can see, I've defined these particular 2 parts are actually the chip parts, which are having a heat generation rate of 10 watts, and have got another heat generation rate of 10 watts. I've got another part combined together, it is generating a generation of 5 watts each, and I've got another product which is generating a temperature, which is having a wattage of around 4 watts. So once I've defined the heat sources, the main heating components inside, then I am trying to define the goals. What is my maximum temperature which is allowed in it? So the goals can be defined in a different ways. I can define by means of surface goals or global goals or volume goals according to your requirement. So here for me the most important one thing was to have a temperature of the particular chip. So I've gone to ahead and I've defined this particular chip. You can see now I've defined this chip. I'm trying to find out the temperature of a solid. What is the maximum temperature of the solid allowed in that chip? And of course, my maximum temperature in the another solid, that is nothing but by another chip. Okay, so that is nothing but my another chip. So this would be the major focus for me, because my limited temperature allowed is not more than 104 degrees centigrade, like what I've mentioned. So I define my things and I go and I run the study. So once I run the study, I get my outputs accordingly to that. So if you can see my cut plots, this is nothing but my velocity plot, but I can just quickly come down and say show me the temperature and say click OK. So now it shows me the temperature for me. So if you want me to change the location of the temperature, what I can do, I can just go and I can just, now you can see this arrow, I can just drag up and down. I can say show preview. It automatically updates me according to my location. So if I change it up, so it automatically updates me the value accordingly to that. If I move it down, it updates the temperature values accordingly to that. So I place my component very smartly down there where my maximum temperature is coming up. So if I wanted to go in and check out, I can, if you can see there, this is something which is on the hotspot. I can say like show me the maximum temperature on the plot. So click on that and show me the maximum minimum temperature on the plot and click on that. So on this plot it is somewhere around 130 degrees centigrade. So you can see the red hotspot is somewhere close on the chip, so it is somewhere close to 130 degrees centigrade. So somewhere like that I have from that particular analysis, what I would understand is, so the maximum temperature is somewhere going close to 130 degrees centigrade. I can also see the flow trajectories if you want. What I can go on, I can just show the flow trajectories. I can just play the trajectories. So you can see basically the fan is sucking in the air from the environmental things and then taking out the hot air out of it from it. So I can basically see how the flow pattern is actually happening inside my enclosure as well. So you can basically give a look at how the air is moving inside to take out the heat out of it. I can just stop the trajectories. The similar way, what I have done the analysis for multiple possibilities, like whatever I have shown to you before, and it's as easy as for me because I don't have to repeat the stuff. Now what I have to do is just right click and say clone the project and change my fan location accordingly to it. So here, firstly, I have to sucking the air, then I have run one analysis by blowing the air. Now I have done another analysis by making by taking a different heat sink with the two fans. I've done another analysis for heat sink 2 by taking two fans. So you can see my configuration changing in it. I have also done multiple studies on that. I have done multiple studies accordingly to that. So once I've done my multiple studies in it, so once I've done my multiple studies in it, I'm trying to find out which would be the better study to me. So for example, one of the examples like what I have taken is for my temperature goal has to be less than or equal to 104 degrees centigrade. But whereas in one of the studies it reports as 117 degrees centigrade. But whereas if you see in this image, I have taken the fan in the middle location, compared to both the heat sinks. Now then I have gone for two fans. Then the SolidWorks reports to me as 108 degrees centigrade with heat sink 3. in this particular example. Then what I've gone is gone for a change in the heat sink, then applied for two different fans. Then it definitely shows temperature way less than what I wanted. It is around close to 97.5 degrees centigrade. So that means it is much lower. Of course, it is good for me, but then I wanted to give a look at whether one fan would be sufficient enough or not. So I've tried with another fan location. So with the different configurations, whatever I have shown to you, I have worked on that and then try to find out which would be the better heat sink design and the better fan location for me, and what kind of fan I have to work with, whether it is a blowing fan or a fan which is throwing air into the electronic enclosure. I have to work on multiple configurations on that. Then now coming up to a conclusion saying like this particular heatsink design with one fan which is at the middle of both the heat sinks can give me a temperature of around 102 degrees centigrade, which would be the 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 best combination or the best one what I could find out according to the configurations and the heatsink designs what I have got, the location of the fans I have got. So at the end, I could definitely come out with the conclusion saying that one fan with heatsink or this particular heatsink can help me out in reaching getting the optimal design of temperature of value at 102 degrees centigrade. So to summarize whatever we have seen now, I could say like SOLIDWORKS Flow Simulation can be applicable in lot of industries. If you can see the images, it can be applicable to a lot of industries. But the best point is, it is easy to use, right? Like I mean to say, you have got a huge database of materials. The environment is not new, and SOLIDWORKS is well known for its easy user interface, and it is still maintaining the same interface in whatever the module you are trying to work. So the learning the tool is not a big challenge. So the learning curve is definitely very small compared to any kind of tool available in the market. And of course, since it is integrated with SolidWorks, like what I mentioned, what if my heatsink is changing? What if my fan location is changing? What if my, we also have a good tool for optimization as well. So if we wanted to work with optimization, we can also do parametric study with respect to my design parameters or flow parameters. We also have a very good tool in electronic called EFD zooming. Now we can definitely show a lot more things. There are a lot more tools, a lot more tools available, so that which can lead to launch your product in a much faster way. So definitely, SolidWorks Flow Simulation can help you in making better decisions at the design phase, so that you can come back and say, okay, whatever I have taken is the whatever the changes have done is validated or not right at the design phase itself. So that's all what I have from my end. I would be open for questions for next few minutes, couple of minutes. So if you have any questions, you are definitely free to ask. I'm open for questions. I don't see any questions popping out. So I would like to say thank you for your interest and participation in the webinar. Now let us know if you have any other further information so that we can come back and discuss in much details for you. Thank you so much.